A very warm welcome to the first lecture of the course on quantum technology and quantum phenomena in macroscopic systems. As the title of the course suggests, that this is a course on quantum mechanics applied to the macroscopic systems and the manipulation of these macroscopic systems for various applications. The outline of this introductory lecture is as follows. Firstly, I will give you a brief historical background of quantum technology. Then I will discuss about the course structure and course plan. It will be followed by informing you about various source materials based on which this course is structured. Finally, I will briefly remind you about some important postulates and mathematical tools of quantum mechanics. This will be helpful for those who are not in touch with quantum mechanics for a long time. You know that quantum mechanics as a conceptual subject is very strange. In fact, Niels Bohr, one of the founding fathers of quantum mechanics, said that without getting dizzy, one can't properly understood quantum mechanics. Erwin Schrödinger, who contributed so immensely for the development of quantum mechanics, even said later in his life that I don't like it and I am sorry I ever had anything to do with it. And you know, Feynman famously said, anyone who thinks they know quantum mechanics does not. In spite of conceptual bizarreness, not a single experiment so far has proved quantum mechanics to be wrong. Rather, quantum mechanics turns out to be quite useful for various technological applications. In a way, it has brought revolution to technology. Quantum mechanics principles are behind the development of lasers, atomic clocks, GPS, the entire field of electronics and computers that we see all around us, internet, and even mobile communications. In all these technologies, the role of quantum mechanics is bit indirect as the system under consideration are not manipulated in the quantum domain. As regards the manipulation of energy levels of atoms, scientists were restricted by the God-given elements which we know are enlisted in the periodic table. So they are limited by these elements only, and one does not have too much of freedom as energy levels of these neutral atoms can be altered or shifted by very tiny amount via application of electric field. You may recall about the Stark effect in this case, or the magnetic field. You may recall about Zeeman effect. And artificial atoms were still to be discovered in the 70s or 60s. However, since 1980s, due to enormous progress in technology and thanks to persistent research by some research groups, it were possible to trap single ion or even trap photons in a cavity, which led to the control of individual quantum systems. Two research groups led by one by Sergei Herose and the other by David J. Wineland contributed hugely towards manipulation of individual quantum systems. Their work in fact revolutionized the technological application aspects of quantum physics, and very deservingly they were awarded the 2012 Physics Nobel Prize. In fact, their works were partly responsible for huge resurgence of research development and towards development of quantum computers. Today, we are said to be in the domain of second generation of quantum technology, where quantum mechanics is going to play direct role in various applications such as quantum sensors, quantum information processing, novel quantum materials, quantum cryptography, and even in the so-called quantum internet. At the core of the quantum technology are the so-called engineered quantum systems such as superconducting electronic circuits, micro and nanomechanical systems, quantum dots, and so on. In this course, we will focus on superconducting circuits, which are discussed as a topic under circuit quantum electrodynamics. Some of you may be aware that Google's latest quantum computer is based on superconducting circuits. Apart from superconducting circuits, we will study micro and nanomechanical systems. They are discussed under the umbrella of cavity optomechanics. These systems has numerous applications. In fact, the LIGO, LARS, which is basically the abbreviation for the Laser Interferometer Gravitational Wave Observatory, in reality is a large cavity optomechanical system. To understand these systems, one needs to know the tools of both quantum optics and condensed matter physics. And this is the major goal of this course, to familiarize you with the essential tools. As I said, in this course we will focus on circuit QED and cavity optomechanics. Circuit QED will be covered in module 2 and cavity optomechanical system will be discussed in module 3. In module 1, we will build up most essential basics right from scratch. This course is essentially application of quantum optics to condensed matter system, and we will discuss all the basics. No knowledge of quantum optics is needed. However, a familiarity with basic quantum mechanics will be helpful but may not be essential. The useful components of the course are that we are going to have supplementary materials time to time, which will help you to, some of you, to familiarize with the concept. Some concept maybe you have forgotten, or maybe you would like to learn it a little bit in more depth. So supplementary materials will hopefully compensate those things, and all the lecture materials would be supplemented by problem solving sessions. After every 3-4 lectures we will have problem solving session. In this problem solving session, sometimes some derivation steps, for example, which may skip in the lecture, maybe we will complete that in the problem solving sessions. And these sessions are going to be useful because you will have confidence as you solve more and more problems, and we will have easy to do assignments based on class lectures. No need for remembering the derivations. You just need to understand how things are work out. So steps are necessary to do, but for examination purposes you need not have to bother about long derivations. The source materials on which this course is relied on are taken from research papers, books, and even from internet. For quantum mechanics, you may look at the book by the elementary book by David Griffiths. 4th edition has come up. Apart from that, there is a little bit on the higher side. That book is by Sakurai's Modern Quantum Mechanics. And for quantum optics, you may look at Introductory Quantum Optics by Gary and Knight. And there's another nice book by Greenberg and Aspect, Introduction to Quantum Optics. It is written by actually 3 authors, Gilbert Greenberg, Elaine Aspect, and Claude Faber. And this book is a bit advanced, that is Quantum Optics by Girish S. Agarwal. And this book is used to discuss some materials in module 3 where we are going to discuss cavity quantum optomechanics. Also, I will rely on or materials I will take from Florian Marquardt's lectures, Marcus Espelmeyer, and I will use some notes by Miskatul Bhattacharya, who is my friend, and he has kindly shared some notes with me. I will use some of them, and I will also use for circuit QED, I will use lectures by Stephen M. Girvin, and also the Kiskit Global Summer School lectures by Zlatko Minev. And there is a very good book on quantum optomechanics. This book is on advanced side, but once you complete the module 3 you will be able to understand lots of the stuffs in this book. This book is called Quantum Optomechanics, written by Warwick P. Bowen and Gerard J. Miller. Let me now remind you about some basic quantum mechanics quickly. While in reality, quantum mechanics happens in laboratory or actual life as put by the quantum physicist S.R. Parrish. To discuss quantum mechanics, we generally rely on the abstract Hilbert space. As you know that in classical mechanics, which I am going to write shortly as CM, the state of a system or a particle is defined by the position and velocity or momentum at a given instant of time. So position, let me denote it by q, velocity by q dot, that is the time derivative of q, and momentum is generally denoted by the symbol p. So if we know the position and momentum of a particle at a given instant of time, then in principle we can predict the past and future of the system by using Newton's laws of motion. However, in quantum mechanics, this is not possible because we cannot know the position and momentum of a system or a particle with absolute accuracy, and there is always a restriction imposed by the so-called Heisenberg uncertainty principle. If the uncertainty in measuring the position is say del q and the momentum is del p, then their product, uncertainty product is greater than or equal to s cross by 2, where s cross is the reduced Planck's constant and it is defined as h divided by 2 pi, where h is the Planck's constant. So we need a completely different mathematical apparatus to discuss quantum mechanics. Here we'll briefly talk about the bare essentials only. To gain some confidence, we shall solve some problems in the next problem solving session. Moreover, I am not being very rigorously perfect while discussing certain concepts. So first of all, let me discuss some important postulates of quantum mechanics based on which the whole quantum mechanics is based. So one of the basic postulates of quantum mechanics says that all you want to know about the system is contained in a complex wave function, and this complex wave function is called wave function, and the wave function contains all the information of the system. So the state of a quantum system is defined by this wave function, which is a complex quantity, and in Hilbert space this wave function can be represented by the so-called state vector, and this is called ket psi, and this notation is due to Dirac. It's called Dirac notation, and this is called ket. And because psi of RT, this wave function is complex, so its complex conjugate would be denoted by psi star of RT, and the corresponding quantity in the Hilbert space or in Dirac notation, it would be denoted by this symbol here, and this is called bra. Okay. Also, it is known that this wave function, if it has to be a valid representation of the system, then it has to be normalized, and that means that this relation has to be satisfied, that integral of modulus of psi of RT d tau, the d tau is the volume, that has to be equal to 1, and physically it means that the probability of finding the particle in the entire volume must be equal to unity, and this quantity psi of RT gives the probability of finding a particle in a small volume element d tau. Small volume element d tau. The corresponding normalization condition in Dirac notation would be simply this. Okay, this is called the inner product or scalar product, and that is equal to scalar product of the state vector with itself, and this is the normalization condition in the Dirac notation. Now, suppose before making a measurement, a quantum system could be considered to be in any arbitrary state, say k psi. Okay, this state psi can be expressed as a superposition of eigenstate accessible to the system. So we can write any arbitrary k as a superposition of eigenstates like say phi 1, phi 2, and so on. If we are talking about a n-dimensional system, that would be Cn phi n. For infinite dimensional system, it will go on. N will tends to infinity, and this we can write it as a shortened notation as Ci phi I. Here phi 1, this phi I is called eigenvector, or it is called basis state or basis vector. In fact, to give you an analogy, as you know, in classical mechanics or in vector analysis, you know that if suppose we have a vector in 3 dimensions, this vector can be written in its component like this: ax I cap. I cap is the unit vector along x direction. Ay j cap. J cap is the unit vector along y direction, and az k cap, and k cap is the unit vector along the z direction. So in 3-dimensional space, you need 3 unit vectors to define the vector. In the similar spirit, you can consider that in n-dimensional Hilbert space, you need n number of eigenstates or the basis vectors to define a arbitrary state vector, say psi. Now it is interesting that all these basis vectors or the eigenvectors, for example, again giving the analogy, here if you take I dot I cap dot I cap is equal to 1. So, and similarly, if you take the product of scalar product of two vectors I cap j cap, then you will get 0. In the similar spirit, again, this vector phi 1, its scalar product with itself is equal to 1. So that means the phi 1 is normalized. But two different state eigenvectors, say phi 1 and phi 2, their scalar product will give 0. And in integral notation, this would be simply phi 1 star phi 1 d tau is equal to 1. And here it would be phi 1 star phi 2 d tau is equal to 0. And in shorthand notation, I can combine both this as say phi I phi j. The scalar product of two eigenstates would be simply delta ij, and delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j. If a measurement is made, the system shall collapse into one of the eigenstates. Okay, so the probability would depend on this coefficient, say C1, C2. For example, say we are in an arbitrary state psi, and if we make a measurement, then the probability that it will collapse into the eigenstate, say phi 4, it would be given by the probability C4 mod square. So in general, the probability, and this is a very important aspect of the postulates, that the probability that system is collapsing into an eigenstate say phi I from psi due to measurement is expressed as, say, pi is the probability that you are going from the arbitrary state psi to the eigenstate phi I, and its probability would be mods of this square, this scalar product mod square, and if you calculate it, you can show that this would be nothing but Ci mod square. Another important postulate of quantum mechanics states that for every physically observable quantity in classical mechanics, there is a corresponding operator in quantum mechanics. For example, if we have this position variable q in classical mechanics, say for position q in classical mechanics, we have the position operator q cap in quantum mechanics. For momentum p in classical mechanics, we have the momentum operator p cap in quantum mechanics, and in coordinate representation we have it as I minus is cross delta q. And for energy E in classical mechanics, we have the Hamiltonian operator in quantum mechanics, and so on. As all the informations are contained in the wave function or the state vector psi, one needs to act on it by appropriate operator to get the relevant information. For example, if I want to know the information about the energy of the system, and when the system is represented by the state vector say psi, then I have to operate on it by the Hamiltonian operator. Then I will be able to know the information about the energy, and generally I end up with a equation of this type, and then this equation is known as the eigenvalue equation. Physically speaking, what happens is that this equation actually means that when I am operating on the state vector psi by the Hamiltonian operator, it amounts to making a measurement on the system to get information about the energy. So it would be basically an energy measurement. Whenever we have equation of this type, say for a physically observable quantity A, we have this operator A cap. It operates on the state vector psi, and if it pops out a value lambda, which is a real quantity, because the observable has to be measurable, so lambda has to be real, and the system remains, the state vector remains unaffected. Whenever this equation is there, this kind of equation is called the eigenvalue problem or eigenvalue equation, which I'm sure all of you know. This is the eigenvalue equation. So in the case of this Hamiltonian, here this, you see, lambda is here the energy. So it is a well-known textbook problem to show that for the eigenvalue lambda to be real, A has to be Hermitian. A must be, this operator A must be Hermitian. Now, another important postulate says that the time evolution of the state vector psi, the time evolution of it is given by the so-called Schrodinger equation, and you know this Schrodinger equation is this one. Time evolution of the state vector is given by the Schrodinger equation. And from this Schrodinger equation, one can immediately write that the state vector at an arbitrary time t is equal to e to the power minus I by h cross h of t psi of 0. And this particular operator, this is an operator, and this is known as the time evolution operator. Okay. One very useful relation in quantum mechanics is the so-called completeness condition. Let me briefly remind you about it, and it is very important relation, completeness relation, or sometimes it is called closure relation also. As you know, any arbitrary state vector, say kate alpha, in the Hilbert space can be expanded in terms of the eigenkets of a Hermitian operator, say A. Then I can write it as a superposition of these eigenstates, say kate I, and these are the coefficients. Okay. Now, if I multiply both sides of this equation by bra j, okay, let me do that. If I apply both sides, then this is a number ci, and I have here ji. Because these are now eigenvector or basis vectors, so I can impose the condition that this is equal to delta ji, and this is Kronecker delta, and from here I get it as Cj. So this implies that this coefficient Ci, I can write it as I alpha. Okay, inner product of I and alpha. So I can now write kate alpha as summation in the place of Ci. Let me write this quantity. This is a number, okay, and I have it here. Because it is a number, I can take it to the other side. So if I do that, I can write it as I alpha. Okay, so this means it is very clear that this summation, this outer product of these eigenvectors, this is actually an identity operator, and this is known as the completeness condition. You can see the utility of the completeness condition when we try to represent an operator in the matrix form. Let us do that. Say we have this operator A, then I can multiply both sides of this operator by an identity. So let me write the first identity as summation of this outer product, sum of the outer products of kate I. Then I have this A, and here it would be sum of the outer products of kate J. So I can do that. Now I can write it as, if I just write only one summation, but actually it is double summation. So in shorthand notation I can write it in this way. So then I have I A J J. Now you see this is just a number, so I can write it here also, I A J I J. There are altogether n square numbers of form IAJ, where n is the dimensionality of the kate space. Of kate space. So we may arrange them into an n by n square matrix such that the column and the row indices appears as follows. So I have this form here. This would be row and this would be column. Let me illustrate it a little bit more clearly. So we will have a n by n matrix for this operator A. So we will have, say, 1A 1. So this is, I can go on writing the first, this bra side here represents the row, first row, and this kth side represents the column. So I have here 1 2, and then I have 1 a 3, and so on. And here I will have this second row a, this is the first column, this is the second row, second column, second row, third column, and so on. And then here I will have third row, first column, third row, second column, actually it would be, yeah, and then you'll have third row, third column, and so on. So we'll have a total n by n. If it is n dimensional, then you will have n square elements. This can be written in shorthand notation as A11, A12, A13, then you'll have A21, A22, A23, you'll have A31, A32, A33, A34, and so on. I hope you are getting the idea. You will have a big matrix depending on the dimension. Okay, we'll give you some example. Let me give you an example right away. Consider a spin half system as an example. Consider a spin half system, and you know a spin half system is a two-dimensional system because it has two eigenstate. One is the spin up state, which is denoted by, say, in this notation, kth up state, or sometimes people write it as plus. This kth, this sign represents that the spin is in the up state, and because it is a two-state system, so this can be written represented by this column vector 1 0, and another state on the other state is the spin down. Spin down state is represented in this notation, and or obviously by this minus, kth minus here, and the column vector would be 0 1. It has to be like this because, as you will see, that these are the kth states, so this has to be normalized. This is the eigenstate, and this is also another eigenstate, so they have to be normalized. And if you write it as 1 0, this is the bra, and it will be 1 0 here, and here it would be 1 0. This is the column, and if you take the multiplication, if you do the matrix multiplication, immediately you will see you will get 1, and you will have minus minus, then here you will have 0 1, and here you have 0 1, and this is also going to give you 1. On the other hand, if you take the scalar product of these two different eigenstates, you can immediately see that it would be 1 0, and this would be 0 1, and if you take the matrix multiplication, it will be 0. So this clearly shows that kth plus and kth minus are orthogonal. Similarly, you will have minus plus is going to give you here to be 0 1, and here to be 1 0, and you will again get 0. So what about the completeness condition? Recall that the completeness condition was this. So in this case, we have, it is two-dimensional, so the kth vectors are plus plus, and you have minus minus, and this would be identity matrix, and you can check it that you will get actually 1 0 0 1, the identity matrix, 2 by 2 matrix you will get. Okay, suppose we have an eigenvalue equation for the spin half system such that if I have an operator, say Sz, if it operates on the up state, then it gives us the eigenvalue h cross by 2 plus h cross by 2, and if it operates on the eigenstate minus, that is the down state, we get the eigenvalue minus h cross by 2. Then we can very easily express sz. So now we can express sz in the matrix form. So it would very easy because we have it would be a 2 by 2 matrix. So elements would be, you have plus sz plus, and here you will have, this is your row, okay, this is your row, this is column, so this will be plus sz minus, and here you will have minus sz plus, and you will have minus sz minus. And now you can work it out because we have sz plus equal, when it operates on it, we are having h cross by 2 plus. If I multiply both sides by the bra plus here, then I will get sz plus, and here it would be h cross by 2. This is what I will get, and this is normalized, so you will have simply h cross by 2. Again, if I do minus sz, if I multiply it by the minus of this bra, then what I will get, you will get h cross by 2 minus plus, and this is orthogonal, so therefore you will get 0. Similarly, you can show that you will have, say, plus sz minus, that would be equal to 0, and you will have minus sz minus, this will give you minus h cross by 2. So therefore the matrix representation of this operator would be, then here you will have h cross by 2, here it would be 0 0 minus h cross by 2, which also you can write it as h cross by 2 1 0 0 minus 1. Many a times we would prefer to work in a particular basis states over that of the other ones. Just like in classical mechanics, sometimes using spherical polar coordinates is more useful or easy to work on than the Cartesian coordinate system. For example, in classical mechanics, whenever in a particular problem there is spherical symmetry in the problem, then we prefer to use the spherical polar coordinate, say r theta phi, rather than Cartesian coordinate x y z, and we can go from Cartesian coordinate system to the spherical polar coordinate system by the so-called coordinate transformation. In the similar spirit, in quantum mechanics, we can go from the basis state, say phi n, to a new basis states phi n dash, or vice versa, and we can do that by using a transformation called unitary transformation. By unitary transformation, we ensure that the probability is conserved. That means that we must have these conditions, that scalar product has to be equal to 1, which is, you know, the normalization condition, and while we go from this, say, old coordinate to new coordinate, this has to be maintained. The scalar product has to be equal to 1. So this is what we mean by unitarity, and this is ensured by unitarity of the transformation matrix. Unitarity of transformation matrix ensures it. Let me elaborate. Let me write, say we have this eigenstate phi n, which I can write because of the completeness condition. Now I can write it as phi m dash, phi m dash. These are basis states, and this is what I have. I can always do that because I know that this is the identity operator. This I can write slightly differently. I can write it, because you see this is just a number, so I can write it as phi m dash phi n phi m dash, and if I write it as summation over m, this is, if I write it as umn phi m dash, where umn is the matrix element of the unitary operator, where I go from the old basis state phi n to a new basis state, say phi m dash. Okay, let me show that u is unitary. To prove it, I just need to show, because u is a unitary matrix, so you know that a matrix is unitary. U is unitary provided u dagger is equal to identity operator. U dagger is the Hermitian operator corresponding to the operator u. So now let me prove it. I have u dagger. If I multiply, if I take this relation, let me work it out, phi m phi n. If I can actually prove that this is equal to delta mn, then it will ensure that u is unitary. Okay, I will show this later. I can write it as phi m, and utilizing the completeness condition, let me put here another basis states, say phi l, like this, and we have u dagger phi n. This then I can write it as summation over l. I can write it as uml u star of nl, where I defined uml is equal to, this is the matrix element of this unitary operator, u phi m phi l, and unl star is equal to phi l u dagger phi n, which is actually phi n u phi l, and if I take the complex conjugate. Now we have uml. This is going from the old basis state, say phi l, to going to the new basis state phi m dash, as per our this definition, which is here. This one you note. Utilizing that, I can write uml like this, and unl star, I can write it as phi l phi n dash. Okay, so therefore I can write sum over this quantity. I can write it as uml unl star is equal to this. I have phi m dash phi l phi l phi n dash, and as you can see, okay, let me write here. I can write it as phi m dash summation over l phi l phi l, and here I have phi n dash, and this is identity operator, so I will have phi m dash phi n dash. So this is the scalar product in the new basis, and we know that this is nothing but delta Kronecker delta mn. So clearly we now have therefore proved that phi m u dagger phi n is equal to delta mn. What it means that this matrix U dagger is equal to identity operator, and which means that U is a unitary matrix. U is unitary. If some of you are finding this particular portion difficult, please don't worry. We will work out a set of example problems in the problem solving session, which would surely boost your confidence. Let me stop here for today. In the next lecture, we will start the course. Please note that you will get some supplementary materials time to time. These are there to help those students who have forgot the basics or those who want to understand certain topics more clearly. Also, please note that if I make some mistakes in the lecture materials, they would be rectified in the problem solving sessions. I hope you will enjoy the course. See you in the next lecture. Thank you.